Okay. So now you know that in conventional furnace, the first slag is over-oxidized. And the only way to reduce this high FeO in the slag is to inject carbon. So that's why I'm not so, let's say, friendly with the practice to burn the door as fast as possible. Because then you facilitate this oxidized slag to escape the furnace. And then you have yield loss on top of more air ingress through the door. So in fact, it's better to keep the door closed as long as possible. Yeah? And then just when you need to take a sample, open the door and clean the door to have access to the bath. But not before having the necessity to take a sample and temperature. Yeah? Because the common practice, especially with the furnace equipped with the BSE lens manipulator, is that they start cleaning the door from the beginning. So it's better to put the pipes in the door and close the door, and that's it. Okay? Alright. So we have seen that we calculate the weight of the silica, the weight of alumina, the weight of CaO. For the other elements, we calculate the content. Yeah? Phosphorus, sulfur, and mangan by the equilibrium, MgO by set point, and Fe by set point. Of course, oxygen is the oxygen linked to the FeO. Yeah? So it's given by the formula. So then, in order to know the weight of the slag, we take the total amount of oxides we have calculated the weight, yeah, CaO, Al2O3, SiO2. Oops. You see these elements here on top, divided by what they represent in the total amount of the slag, which is 1, let's say 100%, minus all the elements where we have calculated the percentage. Is it clear to you?
또 저렇게 계산하나요?
네. 계산 방법이요. 좀 특별한 거 아닌가요?
Because these weights,
Why the MNO is not contained?
no, but we take this this content. You have 26, 27, 28. 26, 27. This is 25, yeah? 26, 27, 28. Okay? 29, this is the oxygen. 30, this is the MNO. And 32, this is the MgO.
Yeah.
Huh? Alright?
좀 나중에 계산식 따라 한번 체크를 찾아서 해보자고. 네, 오케이.
Huh? So then we have the weight of slag. So we can calculate the weight of phosphorus, which is the weight of slag, total slag, times the content. Same for weight of sulfur, weight of iron, weight of oxygen, and weight of MnO. Yeah, MnO is the same. G30, this is the content, times H25, which is the slag weight. Okay?
Yeah.
And you can decay if you want to check.
Yes.
This is 100%, and
Yes.
this is 1000.
19 ton.
Huh?
19 ton.
You checked already, yeah?
No, no.
I believe you. 계속 계산기 두드리니까 이제 물어보는.
저기 아까 퍼센트만 알고 처음에는 웨이트를 모르니까 퍼센트로 환산해갖고 다시 웨이트를 만드는
그렇지,
거죠.
그렇지. 그렇지, 보면 그래서 일단 관련 문헌들은 이제 박사님 돈 받아가지고 좀 그 카피해서 그걸 우리가 지침서 만들 때
네.
이거에서 이렇게 만든다고 지침서 만들면 됩니다.
그렇죠.
박사님 말씀하셔야지.
Okay, so scrap is clear in percentage. Yeah. Then steel is clear in weight and analysis. Dust is given. Slag has been calculated, but we still don't know how much scrap do we need, and we don't know how much carbon powder, CaO, and dolomite. So we have to calculate these weights now. Yeah? Well, for the scrap weight, we calculate first the slag to calculate the yield. I mean, we have to calculate the yield to know, because you see the weight is the tons. Tons in any software from my side, tons mean the tapping capacity, tapping weight. Yeah? Yeah, this is tons here. You see? So this is the tap weight times C4, this is the percentage of scrap, divided by the yield. C19, this is this yield here. Yeah? The scrap yield. So how to calculate the scrap yield? So this is the iron content, C10. Oops, what did I do?
The SI is your function.
Hey?
The macro SI equal SI.
Yeah.
So
This
is
is
your
if.
function.
This is if.
If
function.
아,
Oh, it's a French
French.
Excel. Yeah.
ah,
See.
it's different.
Eh?
Different in English Excel.
Yeah.
Ah,
But I'm sure that in Korean you have it's not a if function you type in. This is your.
we use the English.
Are you using English?
Function. Okay. Can you convert or?
No, it will be automatically converted whenever you will. Yeah,
Ah,
yeah,
okay,
yeah.
okay.
Automatically.
아, 이상하게 써요.
what is 쏘매? 쏘매.
썸에 썸.
아, 썸.
Sum is sum.
Sum.
S-U-M.
Summation 썸에. 썸에.
So, if C4, I mean, if C4 means if I have scrap, I do calculation. If I don't have scrap, I don't do this calculation. This is to avoid to have error by dividing by zero.
Yeah, of course.
So C10 is the iron content of the scrap. Minus C18. C18 is the slag amount generated by this scrap. Yeah? Times G28, this is the FeO content supposed to be the final slag analysis. That means I take here the iron content minus the iron I will lose in the slag. Okay? Minus the iron I will lose as well in the dust. The E column is the dust. You see? E25. E25 is the dust amount times 0.9. Why 0.9? Now I don't remember where I put the 909. And times the iron content of the dust. Yeah? So, again, I have the iron content of the scrap minus the iron I will lose in the slag and in the dust, plus the sum of what will remain in the steel. C26 to C30, 26 to C30. This is these elements here. Yeah.
Yes.
Divided by 0.9 because this is a question of yield. I don't know. Yeah? So I need to calculate the slag generated by this kind of scrap. What you see is that there is a difference. DK will notice immediately that there is a difference between the slag calculated here and the slag calculated here. Right? But this is normal because this is kilogram of slag per ton of scrap.
Yes.
This is kilogram of slag per ton of steel.
Yes.
Right? So you have a difference. So this slag is calculated more or less the same way than down below. That means I take the silicon, which I will oxidize, plus the silica here content in the scrap, time 1 plus basicity. Why? Because 1 represents the silica and basicity represents the CaO I will have to put. Right? So this here is the amount of SiO2 and CaO I will generate in a slag. Yeah? Then C7 is the Mn I will oxidize in MnO. In this case, I don't consider the equilibrium. I just consider that all MnO will be burned, to simplify the calculation. And C15, which is Al2O3. All right? Divided by 1 minus the contents, because here I'm not able to calculate all the composition of the slag. So I just consider that the other element will be decided by the content here in the column G. 28, this is the iron content plus the oxygen which is linked to the iron, and 32 which is the MgO. Okay? Because this is just representing a part of the slag. Is it clear to you?
그래서 저는 따로 우리 식을 보고 정리하면
별도로 생각을 했는데.
그냥 넘어가자. 오케이.
Okay, we need to time to understand that formula. But just go to next step.
I mean, you have to understand clearly, because
Then we need a little more time.
just to because I need to calculate the yield of the scrap. I need to have the slag amount in these metallurgical conditions, right?
Yes.
So the metallurgical condition means the basicity and the iron content. Of course, the scrap yield is not a question of scrap analysis itself. If my target is to have high basicity because I need to make deep dephosphorylation, the yield of the scrap will not be the same than if I have low basicity because I'm just doing rebar. Rebar, construction steel. Yeah.
Rebar.
So, for rebar, I just need 1.8 basicity because tapping temperature is low, and you see? Okay. So the scrap yield doesn't depend only on the scrap analysis. It does as well depend on the metallurgical practice in the furnace.
Yes.
Huh? So that's why the yield is rather easy to understand. This is the iron content minus the iron I will lose. And of course I will lose some iron in the slag. So I need to calculate the slag, and the slag is given by the SiO2 plus CaO plus MnO plus Al2O3. Okay? Exactly like in this part here. Except that in this part MnO is calculated by the equilibrium, what I didn't do here. And these represent only a part of the slag. So is divided by 1 minus the rest of the composition I fixed here, Fe, O, and MgO. And then I have the total composition of the slag. Okay? Is it better? Okay, in detail you will have access to the formula and you make your own cross-check. Yeah? And of course, this is the total amount of oxides and I deduct the dust. So now I know the scrap yield, so I can calculate the scrap quantity. This parameter is just, let's say, is not used for any further calculation. Oh, maybe, but all right, we will see later. Liquid iron would be calculated the same way and derived the same way. Carbon is calculated in the thermal balance. Carbon injection as well, so we will see it later. CaO, you see this is a big number, and dollar line is also a big number because it is calculated by a macro. In fact, you see that I have calculated the request CaO and MgO, and I adjust these amounts here to have difference input output to 0. You see input output. I could have put a formula here, yeah, but it was, let's say, more complicated. It was easier for me to put, let's say, a goal-seek function.
So from the coke to dolomite is we have to use another macro
For?
from the value from the coke.
No. Coke and carbon powder are calculated in the thermal balance. Thermal balance sheet.
And CaO and dolomite is from other macro program.
Yeah. I can show you. It's very easy. Yeah. So in fact here, do you know VBA?
Yeah.
So in the VBA you will find here all the macros related to buttons. For example, you will see the macro behind this button, it will be in the button macros. Yeah? Or here, same. And in electrical power here, same. Yeah? Here I have the data handling macros. So this is to create a file to store the data, then load the macros to load the data in a separate sheet, and save calculation. And the short name, this is a small function I use later. And all the macros are written here. You see the thermal balance. This is a small diagnostic macro to help the user. I will explain later. The electric and the slag adjustment, what we see here. So in the slag adjustment, we have seen this already yesterday. Here, this is the goal-seek function, where we adjust the